Hi, my name is Alistair, and I'm going to do a short talk today on Sylvester, a unified type notation for symbolic mathematics and proof. So when we talk about doing symbolic mathematics today, there are two general program classes. The first is computer algebra systems, and these allow us to do operations like algebraic simplification, expansion, transformation, and rewriting. We do things like symbolic differentiation, integration, linear algebra. We can do things like solutions of different kinds of equations. We can do things like series and limit operations, and we can also do graphical plotting and visualization. So here's an example of a computer algebra system. This is the Maxima CAS. It's a really popular open source computer algebra system. This is Maxima again doing some equation solving and visualization. This is the Mathematica CAS. This is a really popular commercial CAS. And this is SageMath, which actually uses Python as its interactive programming language. This is another popular open source computer algebra system. So the second category of symbolic mathematics programs we can talk about are theorem provers. So with theorem provers, we do things like theorem proving from axioms, inference rules, tactics. We can talk about things like the satisfiability of a Boolean formula. We also do things like constraint solving in integer arithmetic or real arithmetic in the context of optimization problems. So this is an example of a theorem prover. This is the Lean theorem prover. This is actually running inside Visual Studio. Lean is a really popular open source theorem prover. This is Lean again, proving a theorem on prime numbers. This is the Isabelle theorem prover, another popular open source theorem prover. And this is Z3 from Microsoft, which is an SMTP theorem prover. And this is also a really popular solver for doing things like optimization problems and satisfiability problems. Now, if you think about the language of these different symbolic mathematics programs, so in the examples we just saw from Mathematical, Maxima, and SageMath, the languages, they generally tend to be script-oriented. They're untyped or dynamically typed. They're interpreted. They generally lack robust modular namespace support. These are not general purpose programming languages. They are really specialized languages. They tend to lack things like user-defined algebraic data types, classes, operators. Again, they're not really general purpose programming languages. And they can also lack things like first-class functions, pattern matching, sequence comprehensions, and other features of functional programming languages. We can contrast this with theorem provers. Theorem prover languages tend to be really sophisticated and they have features like dependent types, but they tend to have a relatively small developer community and relatively limited commercial adoption compared to more mainstream languages like F# and OCaml, Haskell. So the basic research question that Sylvester tries to answer is, can we use a mainstream functional language like F# as the interactive programming language for both a computer algebra system and a theorem prover? So let's look at Sylvester in action. So this is a Jupyter notebook running on F# kernel. So we're going to load up the Sylvester libraries in our first cell. And the next thing we're going to do is we're going to initialize the Maxima class. So we want to use Maxima as our computer algebra system, but we want to use F# as the interface to Maxima. So we started the external Maxima process. So all we have to do is open up our algebra module. First, we can declare two symbolic variables here we can reuse. So once we declare these variables, we can reuse them. Now, this expression is an F# quotation. An F# quotation, this is the main vehicle of symbolic expression that Sylvester uses. So you see here, this quotation evaluates to this structure. And this structure is really similar to an S expression in Lisp. So there are a lot of different operations we can do on these symbolic expressions. So we can just do a simple simplification. We can also do things like a partial fraction expansion. Okay, here, so we're expanding this as partial fractions with regard to the variable r. Now here we have a simple integer function. This is an ordinary integer function, but by using the formula attribute, we can have access to the symbolic structure of that formula. So if we expand that function f as a quotation, we get the symbolic form of that function. And we can use this function to do things like we can make a numeric sequence from that function. These are just the values we're feeding in. But we can also have a symbol. We can also make a symbolic sequence, and we can also make a symbolic sequence of functions. So this is we're just using the same f function that we just defined, and also a symbolic series of functions. So here we just created a series of functions. So the next thing that we can do is we can try to use Microsoft Z3. So we want to use, again, just like how we use the Maxima CAS as an external tool, we want to use a Z3 solver, but staying within F# as the language. So we create an instance of the Z3 solver. We can then do things like check the satisfiability of a formula. So this particular formula is not satisfiable. There's no integer where the square root of the integer is 2. We can also do things like solve equations. So this equation system is a simple equation system. It has a simple solution. And we can use Z3 to find the solution to that system. So we're using both Maxima and Z3, but we're using it within F# and within Jupyter Notebook. And we're using the same notation, the same syntax for the different expressions, symbolic expressions that we want to operate on. So what we saw basically we can do with Sylvester is we can use F# types, classes, functions, operators, sequences, and other syntactic features to represent these mathematical and logical concepts. We can use F# quotations to represent symbolic formulae and expressions and have access to the symbolic structure of functions and expressions. And we can interoperate with external programs like Maxima and Z3 using metaprogramming. We can run this in any F# environment, whether it's ID like Visual Studio Code or Jupyter Notebook. And later on, we'll see how we can use visualization libraries to actually visualize some things like functions. So one of the things that some of the things Sylvester designed to do is we want to have a unified language for doing these kind of operations in symbolic mathematics and logic. And again, we have a unified interface to these tools, Maxima, Z3, the Prover 9 Theorem prover. And we want to be able to take advantage of the different language tools for F#, Visual Studio Code, Jupyter Notebooks. One thing that Sylvester is not trying to do is we're not trying to do algorithms for high performance numeric computing or algorithms for symbolic computing. We're delegating all of the symbolic operations to programs like Maxima and GAP, to those specialized programs. So let's look at some of the functions in the Sylvester math library. So we can look at, for instance, probability. So in this case, we're using a finite sequence. We create a finite sequence from a set of values. We then create a probability space from the Cartesian product of those values. We use a first class function. We just define P as a probability measure for that particular probability space. And here we define a subset. So we're using F# quotations to define a subset of that particular sample space. And this has a finite cardinality. The size is 6, and then so basically once we have a finite size, we can find the probability of that particular event. And here we just do the same thing we just do another subset. In this case, we're saying we want to find a subset of values where the sum of the two dice rules is 8, and we can just find the probability of that. So these are all types and operators coming from the probability library. And use Sylvester in things like probability. For linear algebra, the interesting thing about linear algebra is that we're actually using type level arithmetic. So we're defining a vector as a vector of length 4. And this particular vector, the type is actually encoded, the length of the vector is encoded into the type. So we have a vector here, we're declaring a matrix as a 3x4 matrix. So this is a fully symbolic matrix. We can use our R variable that we declared above, our symbolic variable. So now, if we try to multiply m by n, now these two are conformable, but if we try to multiply it in the opposite direction, what happens is we get a type error because those actual matrices are actually not conformable for multiplication in that particular order. Now, in this particular, what we do here is we have a vector and we want to augment a matrix with that particular vector. So again, we use this custom operator to be able to create a matrix. So this is actually, we created a 4x4 matrix. We have augmented a 3x4 matrix. So we created this 4x4 matrix by using that custom operator. And again, those operators only work with the particular type level dimensions. So the dimensions don't actually work if these dimensions actually don't match. Okay, so this is the type. So this is getting a type error when you try to multiply it in this we try to multiply this non-conforming way. Okay, so here we have an example of real analysis. And we're doing just things like some different, just as we saw differentiation, integration. Here we're actually doing visualization. We're using the XPlot library to visualize. And again, we're using the same common structure that we used before of expression function that has a symbolic form. Okay, so the very last thing we're going to talk about is just talking about the symbolic logic. So Sylvester uses a theorem prover called SELF, which is an equational logic theorem prover. So SELF is an equational logic theorem prover. It's an LCF style theorem prover where you have particular data structures for theorems, and you're not allowed to construct those data structures or those types if you don't have a valid proof. It uses equational logic, first order logic from a logical approach to discrete math by David Grice and Fred Schneider. And equational logic allows us into easy integration and proof replaying from automatic theorem provers like Proven9 and Metis. So you can just look at an example of symbolic logic here. And so we have a theorem in propositional calculus that we want to prove using SELF. So we're using F-sharp quotations to try and prove this theorem. Okay, so this is our theorem that we want to prove. These are the rules that we use. Okay, and this is the complete proof that gets printed out. Now, in addition to SELF, we can also use Z3 to find counterexamples. So in this particular case, for this particular formula, we see that there's no model that exists for the counterexample. So we know that this particular theorem is a valid theorem, and we see that. So this is just the distributive rule for multiplication over addition. So this particular rule is axiomatically true in the theory of integers that SELF has. So we can try to do another proof of a simple integer formula. But in this case, if we don't complete the proof, then we can't construct a theorem. So this actually throws an exception, just like what LCF theorem provers do, if we don't provide a complete proof. And this is another theorem. This is another theorem in predicate calculus. This is a longer theorem that shows more of the features of SELF, different tactics and rules, and lemmas and things like that. So this is a much longer proof. So what we've seen is we can use F-sharp quotation as a common symbolic notation for symbolic expressions. We can use F-sharp as a language for doing symbolic mathematics and proofs and visualizations. And we can delegate the computer algebra system and logic operations to external tools and libraries, and just use F-sharp as a unified language interface to these tools. And we can contrast how Sylvester does these things with computer algebra systems and theorem provers like Mathematica, Maxima, Sage Math, and Lean. And I think we'll see that in terms of just the language itself is far more capable than the languages of these tools. Sylvester is definitely a viable option, a viable alternative compared to using languages from these tools. So for more information, you can check out the GitHub project, and you can also get me on Twitter at Alistair Bihari. So thank you very much for listening to my talk.